world used to hum. Millions of people walking the streets, honking in traffic, shouting across town. It's quiet now, sometimes too quiet. We lived simple. A farm, a few cows, scraps of the old world. It was just the two of us. And for a while, that was enough. Ellie was small, but she had a fire in her, just like her mother. The kind that made you believe in things again. She gave me hope that this world could be redeemed. The town, if you could still call it that, had a steam mill running off whatever fuel we could find. That place was a lifeline. Every now and then we'd make the trip, sifting through whatever scrap the machines coughed up. She loved that. Like a scavenger hunt, she called it. But she wasn't looking for food or clothes. She wanted gears, wires, circuits. She wanted to build. It started with pieces. A busted actuator here, a stripped bolt there. At first, it was just a game. But then she gave it arms, a voice, a name. She called it Spark. And one morning, I woke up to find it outside, watching the cows. She laughed and said, "Now we've got a real farmhand." She wasn't wrong. That bot, he worked, tended the animals, carried supplies, even played with her. And for a little while, it felt like we had a real family again. But nothing lasts forever. Not in this world. She started getting tired first. Then the cough came. Then the fever. We told ourselves it was nothing. That she'd be fine. But deep down, I knew. She slipped away, just like her mother. And when she was gone, it was just me again. Some days, I wonder if it was worth it. That little bot, still tending the cows, still walking through the fields like he's waiting for her to come back. It seems that's what engineering really is, isn't it? A way to leave something behind. A way to keep going, even after we're gone. It's been a year, maybe two. Hard to keep track anymore. The days blur together, same as they always do. Since Ellie passed, the silence at the farm has been deafening. Even Spark has gone quiet without her there for his maintenance. I could leave him like this. Maybe I should. Maybe it's time to let go. But I don't know if I can. No, not yet. It's not too late. Looks like there's a lot of dust and rust, but nothing is truly broken. Battery's dead. That's all. He just ran out of power. If I want to bring him back, I don't need to fix him. I need to fix the wind turbine. If I can get that running, I will definitely have enough power to charge old Spark. Bearings are locked up. Might be a crack in the stator. Maybe just buildup in the coils. I can't just guess my way through this. Not this time. She used to read this wind turbine textbook more than I ever did. Knew the diagrams by heart. Always said if something broke, there was always a way to fix it. You just had to know where to look. All right, let's see what we've got. A wind turbine is a device that converts the kinetic energy of wind into electrical energy. Wind turbines and wind farms are a major source of renewable energy generation. At a basic level, a wind turbine works by allowing wind to spin large blades. This action provides the mechanical force to drive a generator and produce power. Wind power itself has been used for centuries. Windmills were a technology used to harvest wind to mill grains. In 1891, a Danish scientist and inventor, Paul Lacour, built the world's first wind turbine used to generate electricity. He used the electricity to electrolyze water, producing hydrogen for gas lights in the local schoolhouse. By the late 1890s, the first wind-electric systems were developed in the United States. These early systems laid the foundation for small-scale wind power, primarily used in rural areas where access to central electricity grids was unavailable, helping farms and small towns. During the 1930s and 1940s, wind-electric systems grew rapidly, with hundreds of thousands of small turbines installed across the U.S. These systems provided power to isolated communities, playing a crucial role in rural electrification before grid expansion reached remote areas. In the 1970s, the oil crisis led to a renewed interest in wind power. Financial and regulatory incentives, like the Public Utility Regulatory Policies Act, PURPA, of 1978, encouraged investment, leading to thousands of new wind turbines being installed, mainly in California. By the mid-1980s, tax credits for wind power were terminated, causing the U.S. wind industry to stall. The installation of new turbines nearly stopped, and investment declined as cheaper fossil fuels and grid expansions reduced the need for wind power. Even as U.S. development slowed, wind turbine technology continued improving in Denmark, Germany, and Spain. These countries became leaders in wind energy research, refining turbine designs and improving efficiency, paving the way for future global adoption. Advances in wind turbine blade design have transformed the industry. Modern blades are 90% lighter than those from the 1980s, with innovations like airfoils, passive twist bends, and trailing edge add-ons to improve efficiency, reduce noise, and enhance durability. The 1980s commercial wind turbine blade was much heavier and less aerodynamically efficient. Modern blades benefit from advanced materials and design refinements, allowing for larger turbines that generate more power while reducing stress on the structure. Now to break down what wind turbines are composed of. The rotor blades capture wind energy and convert it into rotational motion. Modern blades are aerodynamically designed, lightweight, and durable to maximize efficiency while minimizing noise and mechanical stress. The nacelle is the housing atop the tower that contains key components like the gearbox, generator, and control systems. It protects these parts from weather and ensures efficient energy conversion from the spinning blades. The gearbox increases the rotational speed from the slow-moving rotor blades to a level suitable for electricity generation. Some turbines use direct drive generators to eliminate the need for a gearbox. The gearbox increases the rotational speed from the slow-moving rotor blades to a level suitable for electricity generation. Some turbines use direct drive generators to eliminate the need for a gearbox. The generator converts mechanical energy from the spinning rotor into electrical energy. Most modern turbines use induction or permanent magnet generators to efficiently produce electricity for the grid. The tower supports the nacelle and rotor at a height where wind speeds are higher and more consistent. Towers are typically made of steel or concrete and can reach over 100 meters for maximum energy capture. The yaw system rotates the nacelle to keep the rotor facing into the wind. This system, often controlled by motors and sensors, ensures that the turbine operates at peak efficiency regardless of wind direction. The pitch control system adjusts the angle of the blades to regulate power output. During high winds, the system turns blades away from the wind to prevent damage and maintain safe operation. The brake system stops the rotor in emergencies or maintenance situations. Mechanical or hydraulic brakes ensure the turbine can be safely shut down during extreme weather or technical failures. The anemometer and wind vane measure wind speed and direction, sending data to the turbine's control system. This helps optimize turbine performance and ensures it adjusts to changing wind conditions. There are four main types of wind turbines in terms of how they connect to the electrical grid. Type 1 is a fixed-speed wind turbine. It operates at a constant speed regardless of wind variations. It uses a squirrel cage induction generator, SCIG, directly connected to the grid. Type 1s are ordinary asynchronous induction generators, usually with fixed capacitance to correct for the reactive power demands. An induction generator is essentially an induction motor, where the slip is negative, i.e., the rotor speed is slightly ahead of the rotating flux in the stator winding. The induction generator has a squirrel cage rotor which draws magnetizing current from the stator, giving rise to a high reactive power demand when fluxing, as when the generator circuit breaker is first closed. Wind turbines with squirrel cage induction generators connected directly to the line are the simplest electrically. While for purposes of aerodynamic efficiency they operate at nearly constant speed, the slight variation of speed with torque and power can significantly reduce mechanical torque transients associated with gusts of wind and grid-side disturbances. Type 2 wind turbines, also known as variable slip or wound rotor induction generators, RIGs, utilize a wound rotor induction generator with external rotor resistance control, allowing for limited speed variation to optimize performance and reduce mechanical stress. Type 2 turbines adjust rotor resistance to control slip, enabling smoother grid integration and improved efficiency in fluctuating wind conditions. This flexibility helps reduce power fluctuations and mechanical wear, making them more reliable for wind farms operating in variable wind speeds. The Type 2 utilizes a wound rotor induction machine, where each of the 3 discrete rotor winding assemblies is electrically accessible via slip rings on the machine shaft. This provides for modification of the rotor circuit quantities and manipulation of the rotor currents, and therefore the electromagnetic torque production. They utilize a system for controlling the magnitude of the rotor currents in the induction generator over the operating speed range. The current controller system usually consists of an external resistor network and a power electronics module that modulates the voltage across the resistors to maintain a commanded rotor current magnitude. The operation of the controller is quite fast, such that it is capable of holding the turbine output power constant for even gusting winds above rated wind speed, and significantly influences the dynamic response of the turbine to disturbances on the grid. Type 3 turbines are sometimes referred to as doubly fed induction generator, DFIG wind turbines, and employ a wound rotor induction generator, where the rotor circuit is coupled to the line terminals through a 4-quadrant power converter. The converter provides for vector, magnitude and phase angle, control of the rotor circuit current, even under dynamic conditions, and substantially widens the operating speed range of the turbine. Flux vector control of rotor currents allows decoupled real and reactive power output, as well as maximized wind power extraction and lowering of mechanical stresses. Since the converter is only handling the power in the rotor circuit, it does not need to be rated at the machine's full output. Turbine speed is primarily controlled by actively adjusting the pitch of the turbine blades. With respect to the grid frequency, power converter can provide nearly instantaneous regulation of its output currents. Under steady operating conditions, the machine-side converter controls the magnitude and phase of currents in the rotor circuit to achieve desired values of electromagnetic torque. Reactive power flow into the line-connected stator terminals of the generator can also be controlled. Field-oriented or vector control of induction machines is a well-known technique used in high-performance industrial drive systems, and its application to wind turbines brings similar advantages. In an earlier version of this turbine, the torque command, and therefore the magnitude of the rotor current component responsible for torque production, was linked to the speed of the machine via a lookup table. The field orientation algorithm effectively creates an algebraic relationship between rotor current and torque and removes the dynamics normally associated with an induction machine. The response of the power converter and control is fast enough to maintain proper alignment of the torque-producing component of the rotor current with the rotor flux, so that the machine remains under relative control even during significant grid disturbances. The line-side converter either absorbs or provides real power to the grid, depending on the operating speed of the generator. If the generator is operating below the synchronous speed for the grid frequency and pole number, real power will flow through the line-side converter to the DC link. The power will then flow from the machine-side power converter into the rotor circuit. If the turbine is operating above synchronous speed, real power will flow in the opposite direction. The stator is connected to the low-voltage side of the wind turbine transformer, but the rotor is a three-phase coil winding connected to a variable frequency power electronic drive via slip rings, rather than an internally short-circuited winding. Active power is drawn from the grid to supply the rotor via an AC-DC and DC-AC voltage source converter link, and the rotor currents can be completely controlled by the IGBT control circuit. The frequency, which the rotor side converter targets, is that which, when superimposed on the rotor speed, gives rise to a synchronously rotating field in the air gap. The active power exchange with the grid is the sum of the power supplied to the grid from the generator stator and the power exchanged with the rotor minus the converter losses. The stator always exports active power to the grid. Type 3 has a number of advantages over the induction generator. The rotor frequency is essentially decoupled from the grid. It can operate over a wider slip range, minus 10% to minus 16%, compared to 0% to minus 2% for an induction generator. The connected doubly fed asynchronous generator wind turbine is not restricted to a single unique operating speed. This allows the blade tip speed to be varied over a range to better match the wind speed and maintain an efficient operating position. Reactive power is controllable. The initial magnetization flux is established from the rotor, while the grid-side VSC still draws only active power. The reactive power is created by the rotor side converter by the firing angle, and thus the field angle relative to the rotating field in the stator. The stator similarly appears as a unity power factor device, even at starting. Where the turbine control system is required to supply or absorb reactive power, the lead or lag of the rotor field can be controlled by the rotor side converter. Since the synchronous rotor field vectors can be shifted angularly, as in the lead and lag of a synchronous machine, the machine can be modeled with direct D and quadrature Q axis components. The phase difference and magnitude of the rotor voltage determine the active and reactive power which is delivered to the terminals of a doubly fed asynchronous generator. In an ideal device, maximum active power exchange takes place at alpha equals 90 degrees or 270 degrees, at which time there is no reactive power exchange. Reactive power exchange is maximized at alpha equals 0 degrees and 180 degrees. The Type 3 can therefore manage active and reactive power independently by controls on the grid and rotor side converters. It requires a converter-inverter arrangement, but the maximum expected power through the converter to or from the rotor is about 25% of the total output power of the generator. Therefore, the converters are cost-effective. There is, however, a downside to the technology. Under serious system fault conditions, the grid voltage may be close to collapse, and attempts to meet a target voltage or power factor will drive very high currents into the rotor, and hence through the power converters. The converters would be thermally damaged by these currents, so the equipment is generally closely protected by an electronic rotor short-circuiting mechanism, often called the crowbar. This can be active within 20 milliseconds and is followed immediately by a machine trip. Conventional synchronous generators supply reactive energy to the fault, and then on fault clearance they participate in the system recovery. Lastly, for Type 4, wind turbines, the generator is connected to a full power converter. In this configuration, a wide range of electrical generator topologies could be employed. Permanent magnet synchronous generator, wound rotor synchronous generator, or wound rotor induction generator. Because all of the power from the turbine is processed by the static power converter, the specific characteristics and dynamics of the electrical generator are effectively isolated from the power grid. Full power conversion means that a back-to-back voltage source converter is connected to the generator. The generator frequency and grid frequency are decoupled by using a voltage source converter. A modern static power converter utilizes power semiconductor devices that are capable of both controlled turn-on as well as turn-off. Further, the device characteristics enable switch transitions to occur very rapidly relative to a single cycle of 60 Hz voltage. Nominal switching frequencies of a couple to several kilohertz are typical. This rapid switching speed, in combination with very powerful and inexpensive digital control, provides several advantages for distributed generation interface applications. Low waveform distortion, with little passive filtering. High performance regulating capability. High conversion efficiency. Fast response to abnormal conditions, including disturbances, such as short circuits on the power system. Capability for reactive power control. Since an individual wind turbine is likely small in rating relative to the short circuit capability of the system to which it is connected, the voltage magnitude at this point will only be slightly influenced by the operation of the turbine. The control scheme, therefore, is designed to directly regulate the currents to be injected into this stiff voltage source. The AC line voltages, DC link voltage, and 2 of the 3 AC line currents for a 3-wire connection are measured and provided to the main controller. The AC voltage and line currents are measured at a high resolution relative to 60 Hz, so that the controller is working with instantaneous values. By comparing the measured DC voltage to the desired value, the controller determines if the real power delivered to the AC system should be increased, decreased, or held at the present value. Such a simple regulation scheme works because there is no electric energy storage in the converter, except for that in the DC filter capacitor. So the energy flowing into the DC side of the converter must be matched at all times to that injected into the AC line. If these quantities do not match, the DC link voltage will either rise or fall, depending on the algebraic sign of the mismatch. The error in the DC voltage is fed into a PI, proportional integral regulator, to generate a value representing the desired RMS magnitude of the AC line currents. Another section of the control is processing the instantaneous value of the AC line voltage to serve as a reference or template for the currents to be produced by the converter. The desired instantaneous value of the line current is computed by multiplying the desired RMS current magnitude by the present value from the template waveform. In the next stage of the control, oftentimes called the modulator section, the desired instantaneous value of line current is compared to the measure value in each phase. The modulator then determines the desired state of the 6 switches in the matrix based on the instantaneous current error in each phase of the line currents. The states are transmitted to the IGBT gate drivers, which then implement the state of each IGBT in the matrix as commanded by the controller. The process is then repeated at the next digital sampling interval of the overall control. The process is repeated thousands of times per single cycle of 60 Hz voltage. By using the line voltage as a template for the shape of the currents to be synthesized, synchronism is assured. Additionally, if there is no intentional phase shift introduced in the control calculations, the currents will be almost precisely, save for small delays introduced by the control itself, in phase with the line voltages for unity power factor operation. Type 1 through Type 4 turbines represent the evolution of wind technology. From fixed-speed induction machines to fully decoupled power converters, each type has progressively improved grid compatibility and energy capture efficiency. Type 1 and 2 turbines laid the foundation for early wind energy deployment, but lacked the flexibility to meet modern grid codes. Type 3 and 4, with their variable speed control and reactive power capabilities, offer far better integration into today's power systems. While Type 3 turbines use partial converters to control rotor currents, Type 4 turbines go further by using full-scale converters. This total decoupling from the grid enables independent control of active and reactive power, ensuring superior performance. As power systems evolve with increasing renewable penetration, the advanced control and fault ride-through capabilities of Type 4 turbines make them the most reliable and grid-friendly option, especially critical in remote and harsh environments. Offshore wind farms face harsher conditions and are located far from shore. Type 4 turbines are ideal for these settings because their full converter design provides robust fault ride-through and grid code compliance, regardless of wind or voltage disturbances. The distance from shore often requires HVDC transmission, which benefits from the grid decoupling provided by Type 4 turbines. Their converters can precisely control power output, making integration with HVDC systems simpler and more efficient. Type 4 turbines enable full variable speed operation, which helps maximize energy capture in the turbulent and unpredictable offshore wind environment. Their converters also minimize mechanical stress, improving reliability and reducing maintenance needs. Finally, offshore wind must maintain power quality under all conditions. Type 4 turbines offer complete control over reactive power and voltage support, ensuring the offshore wind farm acts as a stable and reliable energy source for the onshore grid. Now that we have explained the different types of wind turbines, let's get into how we actually calculate power from wind on a basic level. Wind turbines extract energy from moving air. To design them well, we first need to understand how wind holds energy. These slides begin with the basic concept of kinetic energy and how it becomes usable power through a turbine's rotor. Kinetic energy is 1/2 times mass times velocity squared. This means the energy in wind increases quickly with speed. If air moves faster, its energy grows rapidly. That's why fast winds are so important for generating power efficiently. Power is energy over time. So wind power is 1/2 times the mass flow rate of air times wind speed squared. Mass flow rate means how much air, by weight, passes through a given area every second. That depends on air density and speed. We calculate mass flow rate as air density times area, times wind speed. So the wind power equation becomes 1/2 times air density times area, times wind speed cubed. The cubed term shows how much power depends on fast-moving wind. Because wind speed is cubed, doubling it increases power by 8 times. 1 hour of wind at 20 miles per hour holds the same energy as 8 hours at 10 or 64 hours at 5. This shows how high winds save time and increase output. Most turbines don't even run at low speeds because they wouldn't generate much. Skipping those times doesn't lose much total energy. Instead, turbines wait for strong wind periods where they can deliver far more power with less wear. Wind power also depends on the area the blades sweep. For a normal horizontal turbine, the swept area is pi divided by 4 times the blade diameter squared. That means doubling the blade diameter increases area and power by 4 times. Finally, we will conclude this chapter by discussing how wind turbines are able to extract wind energy. Wind turbines work by extracting energy from wind using lift, just like airplane wings. As air moves faster over the curved top of a blade, its pressure drops. This pressure difference creates lift, which pushes the blade and causes it to rotate. The rotating turbine blade feels wind in 2 ways, directly from the atmosphere and from its own motion. These 2 winds combine, like adding 2 arrows, to create a net flow across the blade that produces lift and drives the rotor. The blade must be twisted from root to tip. That's because the blade moves faster near the tip than at the base. Twisting helps each part of the blade hit the wind at just the right angle to maintain lift across the whole span. Lift depends on something called angle of attack, or how tilted the blade is relative to the wind. Increasing this angle boosts lift up to a point. If it gets too high, airflow separates, and the blade loses lift. This is called a stall. Stall sounds bad, and for planes it is. But for turbines, stall can actually help. When wind is too strong, the turbine needs a way to reduce power. Causing stall reduces lift and protects the system from being overloaded or damaged. There are three main ways turbines manage excess wind: stall control, pitch control, and active stall. Stall-controlled blades are shaped to lose lift at high speeds without moving any parts. These are common in smaller turbines. Pitch-controlled machines use hydraulics to turn the blades slightly. By changing the blade's tilt, the turbine can shed power when winds get too strong. This allows large turbines to stay safe and control how much energy they produce. Active stall combines both ideas. The blades move like in pitch control, but instead of reducing lift, they deliberately increase the angle to cause a stall. This reduces power without needing full shutdown, especially during gusts. To stop the rotor, blades rotate to block the wind. In stall systems, springs in hydraulics flip blade tips sideways. In pitch systems, the entire blade rotates. A mechanical brake then locks the shaft to hold it still during maintenance. In conclusion, wind turbines are elegant machines that turn moving air into electricity by blending physics and engineering. From capturing wind energy with lift, to managing gusts with blade control and stall, each part plays a role in safe, steady power delivery. All right then, I think the textbook gave me enough information that I can try to fix the turbine. Let's see. Looks like the turbine is a Type 3 turbine. Okay, now I see what the problem is. The DC to AC inverter is damaged. I should be able to replace that. I could use that old solar inverter I found. Yes, that should work to get this turbine running. It's working. The turbine is generating power. Couple hours of this and old Spark should be up and running. Spark, can you hear me?
Master Gus, I can hear you. Where is Master Ellie?
Ellie went away. She has gone to be with her mother. 100 years ago, people might have said she's gone to heaven.
Will she ever come back?
No. No, she won't.
Master Gus, can you tell me what death is?
Death. It's like a system failure you can't trace. You hear the hum stop, feel the current fade. But there's no fault code, no breaker to reset. Ellie was like a spark that leapt between wires. Brief. Brilliant. Gone before you ever understood the circuit. But maybe that's the heart of it. Engineering's just a way we rage against time. A blueprint scratched in the dirt to tell the wind we were here. That we tried to hold the world together, even as it falls apart. That's enough of that. Spark, can you do me a favor and project photo album 3?
Affirmative.